Recording is rolling. It is Thursday, October 3rd. Main focus is going to be textbook puzzles. Just over the last few days, we've been doing most of these chapter 4 questions. We're going to switch over. We'll do all the circled chapter 5 questions today. Now, I've had a due date is this coming Monday, but because a lot of students have opted to just go ahead and turn this in at the end of class today, because we will have covered all of them in class. So if you've been in class doing all of them and you want to get them off your hands, you'll be able to do that. Right. At the end of class, I will also get you guys your next take-home quiz on forces and dynamics. Guys, when is the take-home quiz due? Monday. Okay, which you don't quite have yet, but by the end of class, I'll get that to you guys. The plan for tomorrow, I'm gonna have you guys do a lab. I'm gonna have you guys construct one of these Varinon frames. So the purpose of this Varinon frame is, suppose you were trying to figure out what's the optimal location for a factory given different transportation costs. Where should you put it? There's a physics solution to that question. I'll have you guys solve that tomorrow. And then this coming Wednesday, there's a PSAT. So guys, here's the story for this. This is going to affect everybody. Is everybody paying attention here? Right. So this is mostly for 10th graders. Actually, before I hit record, I told you guys if you're in 10th grade where you're testing, I have a whole Excel file for the whole school. There are a few 11th graders. If you think you might be testing, let me know. I can check at the end of class. Right. But this particular classroom is going to be used for testing, actually probably all day. Okay. So all day testing in this classroom. So where are you guys going to relocate on Wednesday? Media Center. Right. Now, actually, I'll be with you guys in the Media Center because I'm not going to be a proctor, or at least not supposed to be. Right. So I'll meet you guys in the Media Center on Wednesday. Okay. Everybody got that? All right. All right. So puzzle time. You guys got your chapter 5 puzzles? Chapter 5 puzzles. Again, if you've been writing all the solutions last few days all along and do these today, then if you want to, you could turn these into the gray tray today and get them off your hands. There you go. So there's 5 circled questions, and we'll have time to do these 5 and have about 5 minutes left over into class. It's gonna work out all great. Number 61. If your textbook is in equilibrium, what can you say about all the forces acting on it? So number 61. Oh, all right, equilibrium. Guys, if you see equilibrium for this class, what can you say about all the forces? All the forces. Yep, they cancel each other out. They equal what? Equal 0? Right. So I'll write this way. The sum of all the forces is equal to 0 newtons. Right? That's equilibrium. Okay. Yeah, let's do a free body diagram. That's a little bit overkill. That's all right. You guys got a textbook. Right. Maybe it's like at rest on a table, or maybe it's at rest, or maybe it's in motion. I don't know. Okay. Let's I bet we could come up with a scenario for each one of those. That could be equilibrium. Okay. Now, suppose it's on a flat surface. Do you think this book has a weight? mg? Weight? Right. But wait a minute, it's not in free fall though. What force is supporting it, holding it up? The normal force. How big should it make that normal force compared to the weight? Same, right? Because of equilibrium, right? That's actually not a Newton's third law pair, because if it was in an elevator, those could be different values. That's okay, right? But it does zero out because of equilibrium. That's this condition right here. Okay. Could that be the entire story? Could that be equilibrium? Yeah, that would be the whole thing. You can walk away from that. That could satisfy it. Right? Or what about this? What if you're pushing the book? Here, let's put an applied force on this. Let's add to the story. What if you're pushing? I got F push. Right. Could that be equilibrium? No. Now there's an unbalanced net force. There's this external net force, pushing force. All right. So if I draw that and walk away, now the book is accelerating. So if I want to put it back into equilibrium, I should probably also include a what force? Friction force. And how long should they make that friction? Same as the pushing force, just got to cancel it out. I call it FFR, friction force. Okay. Right. Now that right there, could the book possibly still be at rest with what I just drew? Maybe, if that's a what kind of friction? Static. Maybe I got my, here, I guess my textbook looks like this now. Or this looks a little bit more like the book. How about that? Right. And maybe I push with a tiny force, but it's not enough to overcome the resistive static force. And so it could still possibly be at rest. Right. But what if it's a kinetic friction and the book is actually in motion? What could you say about its velocity for that free body diagram? The constant. The velocity would be constant because that would still go hand in hand with zero net force, zero acceleration, constant velocity. All right, you guys ready for our next? What are we doing next here? All right, so there's four more to go. Now, two of these, number 97, 98, involve like signs hanging from tension cables. We're gonna save those for very last. Let's hit these two up here. Number 90, 91. 90, 91. Number 90 says you use a horizontal force of 30 newtons to slide a 12-kilogram wooden crate across the floor at constant velocity. Guys, what do you know about the net force for constant velocity? It's equal to 0. All right, let's talk about that. Question. What is the coefficient of friction, coefficient of kinetic friction between the crate and the floor? All right, let's get a picture going. I draw a free body diagram. All right, we'll throw in some force vectors, throw in some numbers, do a calculation here. Let's get a crate. Crate time. I got myself a crate on a floor. All right, throw a center mouse dot on that thing. All right, you guys got a crate. They told you some numbers. We got mass is equal to 12 kilograms. There's the mass of the crate, 12 kilograms. They told you there's a horizontal pushing force, 30 newtons. Okay. So I'll go ahead and throw that on the board because they gave you that. It said F push equals 30 newtons. Okay, so that's what they gave us. Let's set it. Okay. So one more detail is constant velocity. You guys know constant velocity means the acceleration is 0 meters per second squared. It's not changing its motion. Right? Therefore, the sum of forces, the net force, must be 0 newtons. Okay? All right, so with that in mind, let's go finish the free body diagram. FBD, free body diagram. Guys, what's another force acting on that crate? What pulls straight down? Weight. Weight. Okay. And guys, what's the magnitude of this weight? How much? So 12 kilograms is the mass. 12 kilograms goes here. Earth gravity could be 10 meters per second squared. Put it all together. It's how many newtons? 120 newtons. There you go. Okay. Well, wait a minute. It's not plummeting down. What force is holding it up? Normal force, which is equal to how much? 120 newtons, right? So the sum of the forces zeroes out. This could be in the vertical direction, right? That and that cancels vertically. Okay. Now, guys, if I draw that and walk away, could that be constant velocity? No, because there's an unbalanced force. So, okay, so I still need to draw something else to make it constant velocity. Well, what else do I have to draw on it? Friction force. Let's do friction force. Okay. Hey guys, what's the size of that friction force? Same as the pushing, force opposite direction. Okay. So now we've got the sum of the forces is equal to 0 in the horizontal direction. Okay, you see that? Now, if you drew it to scale, I don't think mine's exactly to scale. It's kind of close. Okay. What is 30 compared to 120? Is that a what ratio? 1/4? Okay. If I went back and drew this a little bit better, should the length of this arrow be 1/4 of the length of this vector? Right. Okay. So if this was like 4 centimeters long, maybe this should be 1 centimeter long. All right. So I got that. Now the question was actually, what's the coefficient of friction? The coefficient of kinetic friction. So that's this character right here, mu. I'll do a little subscript k if it's sliding. Right? It's equal to. Now this is a ratio. Guys, coefficient of friction is the ratio of what force over what force? Huh? Yeah, we're comparing the friction force to the normal force. Friction force compared to normal force, right? Just like that? Oh, yeah. Okay. All right. So there you go. There's a formula like straight off one of these posters. Let's get some numbers in here. So we've got a 30 Newton friction force we figured out from the free body diagram. And we've got 120 Newton normal force. Divide those out. All right. 0.2. Guys, 0.25, what unit should I write on that? Can I just leave it? Can I just leave it? Yeah, I can just leave it. That's one of the rare times in physics you could just have a plain number like that. Right? Or if you want to call it Newton per Newton, maybe something like that. Whatever. Either way, you can leave it plain. There you go. There's the coefficient of kinetic friction. Right? And while you guys are finishing writing that one, remind you guys that this is a material property. So if you knew the materials from the outset, then this would be a locked-in number. Like, for example, if they told you this is oak wood and this is like some kind of special tile or something, right? Okay, what's oak wood versus tile? This ratio is going to hold, like regardless of how it's being pushed around. Okay, you guys right? All right, you guys ready for the next one? Number 91. Number 91. A 225 kilogram crate. Okay, so we got another crate. It's a little bit heavier. Or no, yeah, a little bit heavier. Pushed horizontally with a force of 710 newtons. Oh, they're giving us the coefficient of friction as 0.20. Guys, pause right there. 0.20. What is that as a fraction? 1/5? Okay. And based on what we just did, could you guys say the friction force is going to be 1/5 of the normal force? You guys think? I'm just thinking ahead a few steps. Okay. Calculate the acceleration of the crate. Okay, so this crate will have an unbalanced net force, so it's going to accelerate. And how much? So let's try it. I bet it's going to be kind of similar to what we did, except sort of backwards, and we're going to figure out the acceleration at the very end. Okay. So number 91, let's get another crate going. Guys, draw another crate. There's a center mass dot right there. There you go. Drawing a floor for context. We got a floor. Okay. All right. Oh, and what did they tell us? Some numbers. They told us the mass of the crate is 225 kilograms. They also gave us the pushing force. Maybe I'll save that for later. And they told us this coefficient of friction between the crate and the floor. Well, they left it ambiguous, but if it's guys, if it's accelerating, it's got to be what kind of friction? Kinetic or static? Kinetic, because it's sliding, right? So 0.20, right? So they told us that. They also told us the pushing force. And I'm about to be drawing some forces for a free body diagram for some forces, right? Guys, what's the weight of this crate equal to? How many newtons weight? 2,250 newtons, right? So mg, 225 times 10. Okay. Oh, what's the support force from the surface? Called the normal force. How much is that equal to? Yep, 2250 newtons. And you know that because you guys know the sum of the forces in the y direction has to go to 0 newtons. Right? Now, that's not going to be true in the x direction. Right? In the x direction, it's accelerating. So I can say more like this. The sum of the forces in the x direction is equal to mass times acceleration. That's going to be Newton's second law of motion. In the y direction, it's not moving up or down. Right, guys good? All right. Now, here's where they told you there's a horizontal pushing force of 710 newtons. And you know the block is accelerating, so it must be in motion. Right? I like to add all kinds of details and considerations to these. There's actually two different ways you could interpret this at this point. Could you be pushing the crate so that it's moving faster, faster, faster? Could be accelerating that way? Could be doing that. Right? Or what about this? Could it be possible that maybe the crate is already sliding towards you and maybe you apply a resistive force to slow it down? Okay. You could also interpret it that way. I'm going to do the first way that I said. Okay. Let's just go ahead and assume that you're pushing it in a way that's speeding up. Guys, what's 700 compared to 2000? That's approximately what ratio? Is that about a third? About a third? Right. So maybe I should draw this pushing force as about a third of that normal, or a third of these other forces. Right? I'll say F push equals, what was the number exactly? 710 newtons. Right. I think that should be about a third of these other ones each. Right. Pretty close. Right. All right. Oh, now since the coefficient of friction is 1/5, guys, what's 1/5 of say 2000 something? Could that be about 400 something? Right. So I should draw a resistive friction force. I'm assuming this thing is actually moving in the same direction as I'm pushing it. Okay. This resistive friction force should be 1/5 of this normal force. I'll call that friction force right here, FFR, friction. Right? See that's about 1/5 of this because 1/5 is 0.2. Right. Let's get some numbers though. You guys know friction force is coefficient of friction times the normal force, which is 0.20 times what goes right here. Huh? What number? 2250? Okay. 2250, that's newtons. So it's kind of tiny font there. Let's 0.2 times 2250. Okay. Let's get a number. That looks like 450 newtons. There you go. All right. So if I'm comparing the forces that are driving the motion, that's just the horizontal forces, right? The verticals cancel out, whatever. Right. But here's the force to the right. Here is the force to the left. Right? All good? Right versus left? Okay. Now let's do Newton's second law of motion. I'm going to rearrange this and make this in its fraction form. I'll say acceleration is the net force. You guys know sum of forces is the net force divided by the mass. Newton's second law of motion. I'll write that too. Newton's second law of motion. All right? Right there. All right, so the acceleration is big fraction bar. Here, I'll give you guys a head start. What are you guys going to put in the numerator? What are you guys going to put in the denominator? Give you guys a head start. Did you guys write something like this? Right? The difference between right and left is the net force. And that's acting on how much mass? 225 kilograms. Boom, boom. That's true. Does every step make sense along the way? What we're doing? All right. So pause right here because we're about to get the answer. I just got to plug that in the calculator. Okay. So here's what we did. They told you the mass of the block so you can get the weight, mg. If it's a horizontal surface, then the normal force just balances that out. So these two are equal and opposite because of equilibrium. They told you the pushing force horizontal. They gave this number here. Right? They said calculate the, well, they told you the coefficient of friction. Therefore, you can calculate the friction force. So that's coefficient of friction times the normal force. So that's 0.2 times, and the normal force we found was 0.250 newtons. Put it all together. We got the friction force is 450 newtons. Okay? And now we can go figure out something about the motion of the block, the acceleration. So the net force right and left is the difference between 710 to the right and 450 to the left. So calculator, open parenthesis, 710 minus 450. There's the net force, close parenthesis. Okay. Divide by, and that's acting on a mass of 225 kilograms. Put it all together. I'm getting acceleration is 1.16. What? Guys, what's the unit? What's the unit? 1.16 meters per second squared. Oh yeah, because that's an acceleration. Okay. And the assumption I made and the way I drew this and solved it is that it would be speeding up in the same direction that it's moving. Right. It's probably the more obvious interpretation of that question. You guys got 91. That's good. All right, so we just got two circled questions left, and they're both these cable tension questions. We're going to do number 98 first, and then we'll go hit number 97. Okay, number 98 has some symmetry going to it. I got number 98. A street lamp weighs 150 newtons. Guys, pause right there. Who could tell me what is the mass of that street lamp in kilograms? 15? 15? All right. Here's what I'm saying this. You might see maybe this exact question in college, possibly, except they might give you the mass of the street lamp. But if you want, say, a weight force, wouldn't you have to say m times g and brings you back to 150 newtons? Okay. So you might see that. But this book went ahead and gave you the weight, 150 newtons. It's supported by two wires, 120 degrees between those wires. Oh, and then they did add this detail. They said the tensions in the wires are equal. They didn't have to tell you that, although if you start solving it, you probably see that that is true anyway. Even if they didn't tell you, it's still true. What is the tension in each cable? And then, okay, there's a part B where they change the angle. So we're going to save that for later. So let's focus on this first part A. This is 98 part A, 98A. Okay, so with these cables, here's what, here, let me remind you guys that there are posters related to these posters. Right. Do you guys remember truss joint and tension? We're going to basically draw that. Okay. So I've got a street light weighs some amount. I've got a couple of cables being pulled at some angle. Okay. And the guiding principle to solve this goes like this. If you break those diagonal forces into components, the right and the left cancel out. That's what this blue is right here. And the up and the down cancel out. So this up plus this up cancels with the weight pulling down. That zeroes out too. That would put it all in equilibrium. Okay. That's our roadmap. That's our framework. Okay. Right. Now later on, we'll do 97. 97 is maybe more aligned with this one, but if it's asymmetrical. Now we got an alpha and a beta. It's a little bit more complex, but it's the same guiding principle. The sum of the forces in along each axis has to zero out. Okay, so let's try this out then. I'm going to start with those Cartesian axes. Can you guys draw a horizontal axis, dash off a horizontal axis, dash off a vertical axis? All right, guys got a couple of axes, dash, dash. Okay. Maybe I'll go ahead and draw a straight light or something. Something to do with the straight light. It's what, one of these or something. Okay, something like that. Okay. And the origin point, the 0, 0 on your Cartesian system, go ahead and put a big old dot there. I'm going to say that's where all the cables are coming together. So there's one cable pulling straight down, connected to the street light. And that it's going to have a tension in it that represents the weight of the street light. Then there's a cable pulling something to do with up to the left, and a cable to do something up to the right. I kind of want to make my picture really, really pretty. So let me see if I get this exactly right. I know what angles this is going to be too. Boom, boom. Okay, let's try this. So you got cable pulling up to the left and a cable pulling up to the right. About like that. All right, you guys got that so far? All right, the other detail I told you is they told you this angle right here was 120 degrees. All right, everybody good so far? Everybody good? Everybody good? Oh, whoops, I forgot to label the weight of the straight lamp. So can I call this mg equals 150 newtons, like that? All right, I think we're good now. I think we're good. All right, so I think I should break these weights into components. Like this one pulling up to the left. Well, it's kind of up and kind of to the left. So left, up, and then this one kind of up to the right. Well, it's kind of right, kind of up. So right, up. Right. But how much? How much left? How much up? How much right? How much up? So notice I dashed off those components. Do you guys also dash off some components? I'm dashing those vectors because they're components, so I'm not double counting the vectors. There's really only 3 forces. Right? One cable down, one up to the left, one up to the right. Right? But now I'm going to think of it in terms of these components that are aligned with the Cartesian grid. Right? Everybody good so far? Right? Oh, well, let's do a little geometry. Let me label this T and T. There we go. So label tension. I don't know what the tension is. They did. It's the same tension. Right? If I thought those were different tensions, I could call it tension left and tension right, but it's the same. So geometry. Guys, what is this angle right here? And what is this angle right here? How about this? From this line to this line. Huh? Yeah, 30 degrees. Yeah, 30 degrees. There you go. Isn't from plane to plane is 180. Subtract out 120. That leaves you with 60. Divide by 2. It's got to be 30 and 30, right? 30 and 30. Makes sense. Okay. All right, so we got that. All right. Actually, before I get going down this path too far, I want you guys to see a different perspective on this, which also leads to the answer, but maybe a lot faster, kind of. Okay. You guys have actually seen this scenario before. Do you guys remember when I had you guys do that lab where you took some spring scales, you held 2 spring scales up and held 1 weight, and then you spread it out, make it like a Y shape, made it closer to T shape? You guys remember that? Right. And then when I was debriefing that lab, and one thing I did was I point out this exact scenario where there's 120 degrees between those top 2 spring scales, 120 degrees. Okay. Guys, if that's 120 degrees, let's go back to geometry a little bit. What is this angle right here? And this angle right here? Should that be 120 degrees and 120 degrees also to make 360 degrees all in the circle? Right. Now, what I'm trying to get at, this is a little bit alternate approach, but it works specifically for that set of angles. Is, do you guys see that this happens to have radial symmetry? Right. Not just horizontal symmetry, but really radial symmetry. It's 120 degrees between all 3 cables. And if that's true, then does each cable have to be pulling exactly the same to hold it in equilibrium? Which you can get to the answer very quickly from that. I bet some of you guys already know the answer to this question. You can tell me, what is the tension in each one of those cables? 150 newtons. That's it, right? Has to be 150, right? You guys see? Now, really, that only works for this 120 degree angle because of the radial symmetry. Right? Now, are you guys ready to go back, get back on track with the Cartesian coordinate system? Okay, let's go back to that. Right, so here's my system I'm thinking. Is the sum of the forces in the x direction goes to 0 newtons, and the sum of the forces in the y direction goes to 0 newtons. That's kind of my system, although that's really generic. So let's make it more specific to this particular question. Right? Again, you guys know what the final answer is, but we're just doing a different approach here. Right? So how about this component right here? No. Say you go back to the beginning, you don't know what tension is yet, but you do know this 30 degree angle. This component could be equal to what times what? T times sine or cosine of 30 degrees. Cosine, because it's adjacent. Adjacent is cosine. Okay. Oh, is that also true over here? Because of horizontal symmetry, get same tension, same angle. T cosine 30 degrees. You guys see that? Right. Oh, you know what? I don't think it's going to super help us out too much, because this pulling right as much as this pulling left, some value minus itself is just 0 anyway. That's this condition here. The sum of the forces in the x goes to 0. I don't think it's going to really help us solve this. It just confirms something that is true, but it just zeroes out, right? But what about vertical? Can I say this right here is t times sine of 30 degrees? T times sine 30 degrees, right? In fact, I bet some of you guys know what sine of 30 degrees is. Guys, what is sine of 30 degrees? When I hit enter, what does my calculator screen have to say? Aha, 0.5, exactly. It is 1/2, isn't it? Right? That's a good one to know. Right, I bet some of you guys have picked up on that by now. Right? I also call this component just half of t. Just do that. Right? And therefore, this is also half of t. Well, half of this t, but same t. Is that true? All right. Now let's play off this condition right here. The sum of the forces in the y direction goes to 0. Let's make an equation for that for this setup. So I got t sine 30 degrees, which I'll just call 1/2 t, plus this t sine 30 degrees, which is another 1/2 t, right, minus 150 newtons goes to 0 newtons. Right. That right there is this right here. It's the same equation. Right. This is the generic setup. This is with this. Right. You guys remember sine of 30 degrees is 1/2. Put that in parentheses. That's where the 1/2 is coming from, right? Sine of 30 degrees. Right? And we're trying to solve for t. All right, solve for t. Right. Oh, guys, what is half t plus half t? Is that just 1t? Right? Can I slide this 150 newtons over? Look at there. You guys remember a few minutes ago? I asked you guys from a point of view of radial symmetry. And you guys said, oh, well, all the cables are the same, so that the tension has to be 150 newtons. 150, 150, 150, right? And okay, and then I say, well, let's get back on track with the Cartesian coordinate system and try that method, which is right here. And, hey, we're getting the same answer. Ah, right, you guys see that? All good? Good. You guys ready for part B? Part B says, what if we change this 120-degree angle to 90 degrees? Okay. Right. So while you guys are finishing, write that down. Here, ask some questions about, let's say, more conceptual type question about this. Right. So we're about to take this 120 degrees and make it more like 90 degrees, right? You guys see that? We're gonna go from there to like there, right? Which is also part of that mini lab you guys did to kick off this whole section. You guys remember taking 2 spring scales? It started vertical, and there was like some force reading. I bet each force reading was half of the total weight, right? So if these 2 cables were pulled exactly vertical, how much would they read for this street light? How much and how much? 75, 75, right? To balance out with the 150 down, right? And then what you did with your spring scales is you pulled it more like a Y shape and then closer to a T shape. And as you did that, what happened to the reading in the spring scales? They got more and more what? Or whoops, sorry, I gave it away. I didn't mean to. They got bigger and bigger, didn't they? Right? And if you approached a perfect T shape, the spring scale readings would approach what value? Infinity. Ah, remember that? Which might be a hint as to how this is playing out. So if you go back the other way, if you go from 120 degrees to just 90 degrees, what's going to happen to the force rating, do you think? It should go down, shouldn't it? Right? Do you think that part B, which we're about to do, the tension is going to be less than 150 newtons? Right? I think it will be. Well, let's see for sure exactly what it is. 98 part B. Right, you guys ready for part B? Part B. Here we go. So again, I'm going to start by dashing off a couple of axes. Cartesian system. Right, boom, Cartesian system. Center of mass, or sorry, not, well, okay. Here's where all the cables are coming together. Maybe we got a street light down here, something like this. Lights on it, street light. So, okay. All right. It's got the same weight as before. So I'll do mg equals 150 newtons. Same as before, I didn't change. Okay. What is going to change is this angle here. So maybe I got about 45 degrees up to the left and about 45 degrees up to the right. So that this angle between them is now 90 degrees. That's a 90-degree angle right there. Okay. So here's tension. Well, for part B, I'll just call it T again. T for tension. Sometimes to do F sub T for tension force. Geometry. Guys, what is this angle right here? And this angle right here, for that matter. 45 degrees, 45 degrees. Right, that would be. Okay. All right. You guys ready to do components? Components. Let's break the tension into components. Of course, we don't know what the tension is yet. That's okay. We're going to solve for that. But it's kind of pulling left and up, and this one's kind of pulling right and up. So left, up, right, up. Just like that. Right here. Okay. And if you guys wanted a poster to help guide you along, I think this one's hanging in my room. Is it hanging in front of me? Looks about like that. Okay. This is our guiding principle right here. This left and this right cancel out. This up plus this up minus this weight down also zeroes out. That's exactly what we're about to be doing. So the sum of forces in the x direction goes to 0. The sum of forces in the y direction goes to 0. Now, I remember from part A, the sum of the forces in the x direction was not very helpful. And I think that's also going to be true here. I'll label it for completion, but this is t times cosine 45 degrees. And this is t, well, this t now, times cosine of this 45 degrees. Okay. But you guys see this is just going to cancel out horizontally, obviously, but it's not going to help you solve for t, though. Right? Okay. But vertically, ooh, now we do have some vertical information, which is the weight of the street sign, just like before. Okay. Right, so I think this is t times sine of 45 degrees. And this one's t sine 45 degrees. Okay. Does anybody know? I bet maybe somebody knows. What is sine of 45 degrees as a fraction? Does anybody know? It's like √2/2. And as a decimal, it's like 0.707. So I'm going to call this equal to t times root 2 over 2. And same thing here, equals t times root 2 over 2. I mean, you don't have to do that. You could just leave it as sine of 45 degrees. You could write it as a decimal, 0.707. All right, I'll do the fraction form. All right, so let's take this condition right here. The sum of the forces in the y goes to 0. And let's make an equation out of that for this. Okay. So this up, this down, zeros out. Okay. Here, I'll circle them. I care about this one going up, this one going up, and this one pulling down. That all has to zero out. So it's going to go like this. This is root 2 over 2 times t. This one's, so plus root 2 over 2 times t minus this 150 newtons equals 0. Whoops. I ran out of paper. That's okay. Fit it right there. Newtons. Boom, boom. Root 2 over 2t plus root 2 over 2t. Is that just a plain root 2 times t? Okay. Half plus a half is a whole. It's 150 newtons. I can slide that over there. Like that. Right? Last algebra step. Divide down the root 2. Right. 150 divided by the root 2. Okay. Now, before I hit enter, make the connection back to right before I started this one, that 98B. I was asking you guys how it compared to 98A. Right. So just flip back over to revisit this one. Just remember, okay, this angle, the tension was 150 newtons for each cable. And I said, as you pull it more vertically, and you guys said, what would happen to the tension if you pull it more vertically? Gets less, you guys said? Right, so more horizontally is more tension, more vertically is less tension. Right? So does the tension have to be less than 150 newtons? And right here, I'm about to divide 150 newtons by like 1.4 something. Yeah, so it has to be less. Let's get an exact numerical value. I'm getting 106 newtons is the tension in each cable. All right, you guys good? Oh, working. All right, ready for last one. All right, so again, going into this last one, if you've written down all the circled ones over the last few days since we've solved these all in class, if you want to turn these in at the end of class, you can. If you missed something and need a few more days, that's okay too. Okay. Official due date's Monday, that's all right. So 97, and then of course I'll get you guys your take-home quiz right after we finish this one too. Advertising. Joe wishes to hang a sign. Oh, they've got a picture here. Oh, it's Joe's. How much does the sign weigh? 7.50 times 10 to the 2 newtons. Ooh, they broke out some scientific notation. Oh, guys, you normally don't talk like that, but how much does the sign weigh? Oh, 7.50 times 10 to the 2 newtons. Maybe, how could you say this number more colloquially? How many newtons is this? 750, that's what I'm looking for. This is 750 newtons, right? Right. Now, one of the advantages of scientific notation is that you can know exactly the amount of precision that you have. Like, for example, 7.50 times 10 to the 2 newtons. Is this 0 right here? Is that a significant digit? Yes, it is. Yes, it is. That means that we know for sure that it's a 0. Whereas if I just wrote out the number as a whole number, like the number 750, it would be ambiguous. I wouldn't know if it was really 750, if it was 752. It could be 752 is the same as 750. You know, if you don't know that last digit of precision, right? But this way, we know it's exactly 750, or maybe it's like 750.11 or something. That would also be okay because it would still round to 750, right? But I know it's pretty precisely 750 newtons. All right, so here we got a 30-degree angle from the vertical, just like in the figure. The official question is, what's the tension in cable B? What's the tension in cable B? There's also a tension in cable A. We're going to solve for both because we're going to do like a system of equations and we'll just kind of get them both at the same time. So we'll get both tensions. So go ahead, set up a Cartesian system, get a dash off a y-axis, dash off an x-axis. All right, guys, dash off a couple of axes, y and x. Put a dot where all the cables are going to come together. There's a weight of the street sign that pulls straight down. I'll label that mg is 750 newtons. I'll just go ahead and write out the number. That's okay. Right. But remember how I typed it in the book is we know that there are 3 digits of precision. There's also a cable pulling up to the left. I'll call that tension A. Okay. And there's a cable pulling to the right. I'll call that tension B. And boom. Right. No, there's a reason that I knew to draw those arrows, those lengths. Remember, the length of the vector arrow is proportional to the vector magnitude, in this case, the force. Right? How did I know to make this one really short or something like that? Right? Here, I'll show you guys how I know. Let's break this tension A into components. Now, the other forces are already aligned to the coordinate system. Tension B is already horizontal. Tension, the weight is already vertical. I'll leave those alone. But this tension A, I say, well, it's kind of pulling up and it's kind of pulling to the left. Can you guys dash off some components like that? Right? And this angle right here is, how many degrees is this angle? 30 degrees, right? Something like that, 30 degrees. Okay. Okay, now that you got the components, and you also have this framework, the sum of forces in the x direction goes to 0 newtons. The sum of forces in the y direction goes to 0 newtons. Isn't that your system right there, your framework? Okay. Okay. Now you can go back and look at this, and I think this will click if it didn't before. You guys see this upward component and this downward component exactly cancel out? Is that right? And guys, if I pause right there and ask you something about tension A, guys, when we eventually get tension A, which we're about to here in a few minutes, is tension A going to be more than or less than 750 newtons? Huh. How about this? Is this upper component exactly equal to 750 newtons? That's this condition here. This upper component is 750 newtons. Guys, what's the longest side of a right triangle? The hypotenuse? Is this tension A like the hypotenuse of a right triangle? Which is longer than this leg. And if this leg itself is 750 newtons, does this tension have to be more than that? Right? Yeah, I think it's more. Right? I don't know exactly how much more yet. Maybe 800 and something, maybe. I don't know. We're going to find out. Okay. How about this leg of the triangle? Isn't that really short? Because 30 degrees is kind of a small angle. Yeah, right. Well, it's less than 45 degrees. Okay. Does that mean that this tension B is canceling that out? And that's why I drew this really short, right? That's this condition right here. Okay. Right. This right and this left have to cancel out. You guys see that? All right. All good? Okay. All right. Now we don't know tension A and tension B yet, but we've got the right setup. So next step, let's do sine and cosine components. This little bit right here, I could call equal to what times what? Tension A times sine or cosine of 30 degrees? Sine, because it's opposite. Okay. Oh, wait, did we see this one earlier today? Guys, what is sine of 30 degrees equal to? 1/2? Could I do this? Could I call it half of tension A if I wanted to? The same thing, wouldn't it? Right? It's a ratio. Sine and cosine, those are ratio values. This is a special ratio, it's just 1/2. Right? How about this component right here? Tension A times cosine of 30 degrees. I guess since I'm doing ratios, does anybody know what is cosine of 30 degrees as a ratio? It's like √3/2. Right, so, right. Or okay, you could just leave it as cosine of 30 degrees. You could do what I did, the ratio. You could write out the decimal if you wanted to. I think here, let's see, what is that? √3 divided by 2 is like 0.866. So if you wanted to do that, you could call it that 0.866. That's good. All right. So I got my components. Now let's set up a system of equations here. I got the general framework, but let's do an equation for each one for this puzzle. In the x direction, I have tension B pulling to the right, minus this component pulling to the left, that's half of tension A. That has to zero out. There's one of my equations that comes straight from this. Right there. How about in the vertical direction? What's that going to be? Well, I got this pulling up. That's like root 3 on 2 of tension A. Minus this weight down, which is 750 newtons, is equal to 0 newtons. So there's horizontal, there's vertical. And I can think of this like a system of equations. Right. Now, if here, break out my poster. I was saying this poster here is kind of what we're going for. Oh, hey, look, that's what I just did. Sum of forces X, sum of forces Y, each goes to 0 newtons. Okay. Now, this one's a little bit more complicated because there's nothing, there's no cable that's pointing exactly horizontal. They're both diagonal, right? Something like that. Okay. You would have to solve this with both equations in conjunction with each other. That might involve substitution, it might involve elimination, might involve a matrix. You just pick your favorite algebra method. But you know what? The fact that one of these cables is horizontal, do you guys see that one of these equations will directly lead to one of the tensions right away? Can we solve for tension A with just this bottom equation alone? I think we can do that. Let's do that. So let's take this one right here. I'm going to slide over the 750 newtons, say root 3 on 2, tension A is 750 newtons times 2 divided by root 3. 750 times 2 on the root 3. Tension A is 866 newtons. Okay. Now that's not the one the book asked, but hey, that does confirm something that we were saying earlier. Remember, I asked you guys, I said, is tension A more than or less than the weight of the sign, 750 newtons? And then we kind of reasoned through it and said, well, I do see some triangle geometry. It's got hypotenuse, longest side. It's got to be more than. It's got to be more than 750 newtons. This is 750. Bounce it. This 750. Hypotenuse is longer than that. It sure is, isn't it? I said it's probably 800 something. There it is. Okay. All right, you guys good? Okay. Now the question we really got to chase down is, what is tension B? Can I take this tension A and this equation, bring those two together? I got tension B minus half of tension A. So here's tension A. Well, I'll call it tension A, but I know it's 866. Has to zero out. Is that true? I just copied this equation straight up. Then where tension A goes, I'm going to plug in 866 newtons because that's what that is. Okay. And then just add that over. Now I've got enough paper for like one more line. I'm just going to write the answer. Tension B equals. Okay. Guys, what's the answer? 433 newtons. Exactly. All right. And that closes out the chapter 5 puzzles. All right, guys, good? It's good? All right. So here in the last few minutes, yeah, okay, perfect. We got about 5 minutes left in class. So I need to get you guys your take-home quiz, which is due when? When is your take-home quiz due? Monday, right? And these puzzles, if you want to turn them in right now, you can. If you got them all from the last few days, if you need an extra couple days, that's all right too. That's a close on the recording.